This guy is posted this year, in its classical web, which is like a good source. Right?
Okay, let's get started. So today we'll be doing the topic 2 review. Topic 2 functions. I think topic 2 functions is a lot of overlap with the calculus part. So it'll be basically just reviewing the shapes and characteristics of various types of functions, and also some key features and equation solving methods and stuff like that. So, okay. All right, let's get started with the little cheat sheet. So once again, just like yesterday, I think we can divide this topic 2 into multiple categories, multiple like chapters if I wanted to. The first is the equation of a straight line. And then we have the inverse function. Also the composite function. As well as the quadratic function and equation. Also we have the inequality, I think. Rational function. Rational function. As well as exponential and logarithmic function. We also have equation solving, polynomial function, and inequality, and lastly the absolute function. So hopefully I'll be going through an average one chapter in like 6 minutes. We'll see how that goes. But some chapters are significantly shorter, so it's fine. Right. So let's start with the equation of a straight line. Well, we all know that equation of a straight line. I'm not going to like even write down too much, but for the equation of a straight line, we just forget the fact that we have 3 different versions of it, right? So we have the gradient intercept form, which is the y equals mx plus c style. And also the point gradient form, by the way, we already have them in the form of the booklet, but I don't think there's a name for it though, so that's fine. You don't have to memorize the names, that's fine. And also the general form, which goes as ax plus by plus d is equal to 0. So we have these 3 styles, so just knowing what to do, how to find these are pretty straightforward. These are, and I misspelled straight, not Hasmus. Okay. So starting from here, we just know that there are 3 ways of representing the equation of a straight line. Now, if you know that, that's enough. Moving on to the next part. The plus d.
Yeah.
The plus d determines the position of the line. So if you change the d value, if you keep the a and b value the same, but the d value changes, then you move the graph up and down and sideways. Let's talk about the inverse function. So there are 2 ways to understand the inverse function. One method is to think about the y and x swapping. Right? So you replace the position, and then it's easier if you isolate y again. Right? So for example, if you have a function like an equation or a function like y is equal to, let's say, x power of 2. It's not a good one. Let's do another one. 3x minus 2, let's say. Then we just replace the x and y, we swap x and y. 3y minus 2. Then you isolate the y, x plus 2, and then divide it by 3. This y is going to be x plus 2 divided by 3. We can say that y equals 3x minus 2 and y equals x plus 2 over 3 are an inverse function. Okay. The example that I was about to write for y equals x squared, if you do the similar thing, it seems like it's working, but then when you square root x, it becomes a plus and minus, right? So in that case, we say that y equals x squared does not have an inverse function, or the inverse relation is not a function. So this one, we fail the horizontal line test. Horizontal line test is similar to the vertical line test, but just like how the vertical line test tests whether a relation is a function or not, horizontal line test tests whether the inverse function exists or not. Okay. The arrow would be better here. So you can imagine the graph of y equals x squared. If you do a horizontal line test, you have multiple intersections. So then it does not have an inverse function, unless you restrict the domain. So that's one way to think about it. Another way to think about it is to think about it graphically. Is a reflection over y equals x. So you can find the inverse function by doing the reflection over y equals x. For example, let's say we have a function like this. It's an exponential function. Let's say this is y equals e to the power of x. Then we can find the inverse function of it by reflecting over y equals x. So then the new graph will look like this. Like this. Which we know that is y equals to ln of x. So those are two ways that we interpret the inverse function. Any questions about this one?
How would you do like reflection over a point? Like let's say like 0, 0 or something. Reflection of that over 0, 0.
You can.
Yeah, so 0, if it's on the y equals x, which it's an invariant point. Yeah. And the other points, well, right now I just drew it just as I'm seeing it, but technically what you're doing is, you know that for y equals e to the power of x, we have a point like 0 and 1, right?
Yeah.
That point, when we reflect it over y equals x, what we're doing is we're swapping x and y. Once again, just like the above, we're swapping x and y, so we have the same point as 1 and 0. So that's how we do that over and over again to completely reflect it over y equals x. Okay. This inverse function is used when we're doing the finding the area under the curve, or finding the area with the y-axis as one boundary, right? In the calculus part. So that's also useful there. Otherwise, let's move on to the next part. Number 3 was composite function. Composite function is when you have a function of a function, right? So we usually represent it as either f of g of x, or we also represent it as f with a little circle, f g of x. Basically, we can also do the evaluation such as like, let's say f of x is, let's say 2x plus 1, make it easy. And then we can also find the f of, let's say 3x squared, for example. Then it means that we're replacing the x and the f of x. We just replace that with whatever input you have. Just make sure you put a bracket around it, right? So we'll do the 2 times bracket 3x squared plus 1. So then we can evaluate this to be 6x squared plus 1. So that's the idea of the composite function. The composite function is used in the calculus once again when we do the chain rule. So noticing that you have a function inside a function is quite helpful, and a good practice is to identify what is f of x and what is g of x. For example, let's say we have something like sine. It's an easy example, but sine of x squared, let's say. Right? And you know what? Let's take it one step further. Let's make it like this. I don't know. Then what I'm going to say is that, hey, let's call this x squared as h of x. Okay? then I can rewrite this into sine of h of x. Then let's call the sine of x to be g of x. G of x is equal to sine of x. So then this is going to be g of h of x. And then let's call f of x equals to square root of x. So then we can write this as f of g of h of x. Right? Then when I'm doing the chain rule, the life gets slightly easier. Okay? Because no one likes to deal with the square root of sine of x squared. That's too much. So identify the h of x, g of x, and f of x. That's helpful. Okay. Any questions about this? It's a pretty straightforward topic, although a lot of people struggle, but we're all grade 12, so it's fine. Okay, let's move on. Number 4 is the fun part, quadratic function. So quadratic function has some characteristics. Well, first and foremost, just like the equation of a straight line, we have 3 different representation. The first one is the ax squared plus bx plus c, which is the general form. We also have the a times x minus h squared plus k, which is called the vertex form. And C, we have the a times x minus m times x minus n, which is the factored form. Some characteristics of a quadratic function is that we have a vertex, right? So a vertex is one of the key aspects, the main characters of the quadratic function. This vertex can either be a maximum or a minimum, depending on what a value we have, right? The a value determines the coefficient of x squared. A value determines the direction the graph is facing, either upwards or downwards. If it's facing upwards, it's positive, so then we have a vertex of a negative. If it's negative, we have a vertex of a maximum, and it's facing downwards. That's an opening on the downward side. Another characteristic is the number of x-intercepts. The number of x-intercepts are determined by looking at the discriminant. The discriminant is equal to b squared minus 4ac. You find the discriminant, is it in the form of a book?
Yeah.
Yeah. The discriminant tells you it's underneath the square root, right? So if it's positive, it means that our quadratic formula works well, right? So we have 2 solutions. If it's equal to 0, then it's square root of 0, so plus and minus has no effect, so we have only 1 solution, right? If it's greater than 0, 2. If it's equal to 1, if it's equal to 0, 1. If it's less than 0, we have 0 real solutions. Of course, we'll see later that we actually have 2 solutions all the way around, but sometimes we have real or non-real solutions. But in this case, 2 real solutions, 1 real solution, and 0 real solutions.
For the vertex form, H was what was H and K?
Right, so in the vertex form, the H and K is the coordinate of the vertex. And also, in the factored form, x equals m and n are the x-intercepts, and also they're the roots, the zeros, and stuff like that. Just like how we have 3 ways of solving the quadratic function, of representing a quadratic function, we also have 3 ways of solving quadratic equations. So solving quadratic equations from y ax squared plus bx plus c equals 0. So one way is to use a quadratic formula. Complicated looking, but probably definitely the easiest one because you just plug in the values, right? Negative b plus minus b squared minus 4ac divided by 2a, which is available in your formal booklet, so it's quite handy. And also it calculates, it always works, right? Another method is to complete the square. where we try to represent our answer as 0 is equal to ax minus h minus h to the power of 2 plus k, right? And then we just step by step we solve it, which is not a good idea. You never want to do to complete the square. Whereas the last one is the factor, the expression, into 0 is equal to a times x minus m times x minus n into a factored form, and then we just immediately know that x is equal to m and n, right? So this is easy when you have a quadratic expression that's easy to factor, especially sometimes when you have a value of 1, or if itself everything is simple enough.
How do you complete the square again?
Complete the square. Let's do one example. Should I?
Yeah.
I don't want to, but let's do one.
Well, it's sometimes useful for some questions. I don't know if
I
it's
have
the
never
IB
used it in the 2 years of math, except that one question that Ms. Key put.
I don't know if it's useful in the IB curriculum, but in Turkey we used to use it sometimes for problem solving.
Are you from Turkey?
Yeah.
I didn't know that. So what I do first is I put brackets around the first two terms, and then I find the b value, the 4, I divide it by 2 and then square it. So in this case, it's going to be plus 4, right? I can't do just plus 4, so I do minus 4 as well. Minus x is equal to 0, x squared plus 4x plus 4, and then the minus 4 leaves the bracket, so it's going to be minus 4 minus 6, so minus 10 equals 0. So that's x plus 2 squared. 10. And then square root both sides, it's going to be x plus 2 is equal to plus minus square root of 10, and x is negative 2 plus minus square root of 10. Yeah, and once again, don't use it. Right?
Yeah.
Don't do that. Use quadratic formula. Quadratic formula is basically a generalized version of completing the square.
And it's way easier.
Way easier.
Okay.
Okay, so that's what we did for the solving quadratic equations. Look at my cheat sheets one more time. 3 types of equations: vertex, minimax, and axis of symmetry. And factoring, completing the square, quadratic formula. Okay, I did everything except the axis of symmetry. Another thing about the quadratic function is that when you graph it, it has a parabolic shape, right? So let's get a graph of it. It usually has a shape like this. It's parabolic. Parabolic means that we have a vertex that has a turning point. And also another thing to note is that it has an axis of symmetry. So that axis of symmetry is found by doing x equals h. X equals h is a vertical line going through the x value of the vertex. So if you know the h value, if you can put it into a vertex form by doing the complete the square, then you can find the axis of symmetry. Or you can just find it by doing x equals negative b over 2a. Okay, you can also do that. Is that in the form of Euclid?
It is, yes. What was this useful for?
Nothing much.
Just to calculate it.
Yeah, axis of symmetry is x equals negative b over 2a. So yes, it is in the form of Euclid. Yay. Right. I think that's about it for the quadratic function. Yeah.
How do we come to negative b over 2a?
Negative b over 2a.
Do the quadratic formula.
Yeah.
Yeah. So if you look at the quadratic formula, axis of symmetry is the middle, right? So it's kind of the middle point of the plus and minus, because it's plus and minus the same value, right? So you know that distance, because it's symmetric, this distance and this distance are the same, right? And actually, if you measure that distance, it's going to be square root, you don't have to know this. This distance is square root of b squared minus 4ac over 2a. Right? So from the axis of symmetry, you do plus square root of b squared minus 4ac over 2a, and that is the one x-intercept. And if you do minus that, that's another x-intercept. No one says no one says this. No one measures that distance like that, though. So don't worry about it. Yeah. Okay, let's move on to the next part. After quadratic function in equation is let's talk about the rational function. Oh, fun stuff. Rational function. So rational function is when you have a y is equal to f of x divided by the g of x. Right? When you have something on the bottom, when you have x on the bottom and x on the top, you don't have to have x on the top. If you have an x on the bottom, then we call it a rational function. Because of the nature of the rational function, is we're very likely to confront ourselves with the vertical asymptotes and the horizontal asymptotes. So the vertical asymptotes, we can find it by solving the g of x is equal to 0. Right? The g of x is the function that goes on the bottom. So if you're dividing by 0, we know that the function does not exist. The y value does not exist. That's why we have a vertical asymptote. And how do you find the horizontal asymptotes? Now we know the limit. We can simply find the limit as x goes to infinity of f of x over g of x. And the limit as x goes to negative infinity as well. Then we can find the horizontal asymptotes. The best is if you graph the vertical asymptotes, graph the points, and it'll kind of make sense on its own. Okay. Another thing to think about when we have the rational function is that we need to think about which side is heavier and which side is lighter. Right? Heavier and lighter, it means like if you have a rational function with the polynomial functions on the top and bottom, then whichever side has the higher degree. So if you have a case where it's something like, let's say 2x minus 1 over, let's say 3x plus 3, let's say, for example, then this is the same weight. Right? So we have the usual case of a function like going like this. Right? It's not graph like this. Let's say a function like this, a function like this. We have a vertical asymptote, we have a horizontal asymptote. Everything is normal. Sometimes you'll be seeing some functions like, let's say 2x squared plus 3x plus 1 is equal to over x minus 2 sometimes. Then this side, the top side's heavier. Then this time we're going to have a function that goes like this. So this time we have an oblique asymptote.
That's the name.
If I can spell it. Oblique. And we still have a vertical asymptote. So we either have a function like this, or we also could have a function like this. Either the red one or the black one. And lastly, of course, we can have a function where the bottom side is heavier. Then this time we don't have the oblique asymptote, we just have multiple vertical asymptotes. Depends on the shape, but maybe you may have a case like multiple vertical asymptotes. So the function goes like this, like this, like this, or something like this.
How do you know how to draw them? Do you just put random numbers in it?
Right. So my suggestion is after you first find the vertical asymptotes, you try to plot some points before and after the vertical asymptotes. For example, let's do another one. Instead of 2x squared plus 3x plus 1, let's do like x plus 1 divided by x minus 2 times x plus 2, let's say, hypothetically. Then what I'm going to do is I'm going to draw out, let's go like this. And then I know that it's x minus 2 and x plus 2, so if I solve the denominator, I know that at x equals 2 and x equals negative 2, I'll have the vertical asymptotes, right? And then I'll simply just plot some points. I'm going to test x equals 0. What is the value of y when x equals 0? Well, it's going to be 1 over negative 4, is it? 1 over negative 4. So we have a point here. And then I can try some other numbers too. Like I can try 1. I can also try negative 1 to look at the trend. Should I? Why not? So if x equals 1, it's going to be 2 over negative 1 times 3, negative 3. 2 over negative 3, negative 2 over 3. So this time it's going
Goes
to be
down.
like, goes down. 2 over negative 3. It's going to be like this. And then let's try negative 1. It's going to be 0. Oh, that's kind of weird. If it's x equals negative 1, what's
Should
that?
go like. pew,
So I think it goes like
up.
like
Yeah.
this, probably.
Oh, okay.
And then let's try a value before negative 3 and after so before negative 2 and after 2. And I can do the same thing to plot the points and see the general trend. I don't need to do too many, but a few is required.
So does it not need to have a horizontal asymptote?
Oh,
It's 0. Why? It's y equals 0.
you like
For this case, it isn't.
It is. It still is.
I think it's 0. Yeah, it's 0. X, y is 0.
Yeah, no, because the middle part of the function is going through is like y equals 0. Is it still?
Yeah, so
the
it's kind
outsides, yeah, but like.
it's kind of weird. Yeah, so
How
it
do you
depends on the
define it?
zones, right? On the outside, yes, there's a horizontal asymptote because we have a graph that reaches that 0
Yeah.
in long term, right?
Yeah.
But then, yes, inside it's kind of weird. It goes through that point.
Okay.
I think we still describe it as there is a horizontal asymptote, just not inside that zone. So these are the characteristics of a. I think it's going to be like this. I'm not too sure. That's my intuition. But yeah, but these are the characteristics of a rational function. We have a lot of asymptotes. Okay. Any questions about the rational function? Let's see if I've missed anything. Vertical and horizontal asymptote, non-permissible values. Yeah, non-permissible values. So non-permissible values happens when you are able to cancel out some factors, right? So for example, let's say we have y equals, let's say x plus 1 times x minus 1 divided by x minus 1. Right? Let's say you have a function like this. Then originally it looks like a function with a heavier top, but then you see that x minus 1 are cancelled out, right? So then it's now just y equals x plus 1. All right, well that's fine. So we just have a function, it's a linear function that goes like this, right? Is it? Not really. Right? So it's similar to that, but then we're gonna have a hole. So that you can think of it as that the ghost of x minus 1 kind of lingers around and it's just gonna hunt you even after you're dead. So that the graph is similar to the linear equation, but except we just have a non-permissive value at x equals 1. So we have that, we say that it's non-permissible value x equals 1. Or we can just define it as domain as well. So sometimes we have those cases, but mostly it's going to have those weird shapes of oblique asymptotes. All right, very good. All right, so let's move on to the next part, which is, we're done halfway, but harder parts are coming. Exponential and logarithmic function. So exponential function and logarithmic function, each of them, they have a horizontal asymptote and a vertical asymptote as well. Exponential function has a shape that goes like this, usually, for the, let's say this is y equals e to the power of x. In the exponential function, the basis, usually the base is e, the natural number. And also we have the logarithmic function that goes like this. We usually have the case of like ln of x. Okay. So for the y equals e to the power of x, we have the horizontal asymptote of the y equals 0. And then for the logarithmic function, we have the vertical asymptote of x equals 0. One thing to note is that depending on the value of the base, the function can change the directions it's facing and whatnot, right? For example, if I want to graph y equals 1 over 2 to the power of x, then I think the function kind of looks like this kind of style. And it's kind of, if you think about it for a second, it's basically the case of kind of like a geometric sequence with a common ratio of 1 over 2.
Yeah.
Right? Not really, but kind of. So then you can imagine that the values are dropping infinitely towards 0. Okay. So be mindful of those cases. And once again, as mentioned before, we know that the exponential function and the logarithmic function usually have that inverse relation, which can be seen by drawing the y equals x reflection, a line of symmetry, axis of symmetry as well. Okay. Nothing much to mention here, nothing in the form of as well. Oh yeah, so there are some conversion stuff, usual. Oh, the one that we did yesterday, it's right here. X equals a to the power of log base of a of x. Huh. I never knew this.
What does this mean?
Which one?
Remember yesterday when we were reviewing a logarithm?
Yeah.
We had a case, oh, when you have these like a to the power of log base of a of x, that's just x, right?
Yeah.
We had that.
Because the exponent in the inside of the logarithm, you just take it out
Yeah.
and multiply it, and log base a is 1. So it's,
Yeah.
that's
funny. I never thought of looking here.
that's cool.
Anyways, let's move on, unless you have another questions. Shape of negative and fraction base, we saw that. And y-intercept and x-intercept, we also saw that. Y-axis, y asymptotes and x-intercepts. Okay. Any other parts? Let's move on. Number 7.
I have
I have a feeling maybe we'll go home today early.
Blasphemy.
All right, number 7, equation solving. Another relatively easy one. So the topic here is that we have 2 methods of solving equations, right? We have the analytical solution, which is synonymous of saying the algebraical. And then we have the graphical solution. So analytical solution is by hands. So, and also by, you can find the exact values, right? To solve things analytically, we need to use our skills in algebra, right? Such as factoring, completing the square, things like that, or using a specific formula, or whatever that is, right? For the graphical solution is we use by calculator, and therefore quite often we'll have to use the approximate values. There are some types of graphical solutions we can use. One method is just to do the left-hand side is equal to the right-hand side rule. Right? So this means that, let's say you have an equation like f of x is equal to g of x. And by the way, the left-hand side or right-hand side, it can be it doesn't have to be in terms of x, right?
Is this for graphical? Or
Graphical, yeah. Then what we do is we say that y1 is equal to f of x, and y2 is equal to g of x. You graph it, and then you find the point of intersection.
Did you just say, Mr. Yi, that both of them they don't need to be of x, or what did I mishear?
Yeah, one second. Just one more time. When you find the point of intersection between the f of x and g of x, the answer is going to be the answer is going to be the x coordinate, right? You don't want the y coordinate. Y coordinate has no meanings in this equation. What I meant by one of them can be not related to this is, for example, you could have a function like x squared plus 3x is equal to 5. Right? So one side doesn't have to be in terms of x.
Okay.
You can still use it, right? So you can still do y1 is equal to x squared plus 3x, y2 is 5, and it still works. Even if it's 0, I suggest that we use the left hand side is equal to right hand side method. On the second line, just type in y equals 0, and you find the point of intersection. The other way is to like put them into one side. So that's one way. The second way is to, when you have f of x equals g of x, I don't know why anyone would do this, but you say f of x minus g of x equals to 0, and then find the x-intercept. That's one way to do it too. But finding the x-intercepts requires more clicks on your calculator, so I don't like doing it. You have to go left bound and the right bound and then capture the point and blah blah blah. That's why I don't like it.
But
If you do second trace, you just go to the point and click.
And whereas the point of intersection, if you just go near, you find it right away.
Oh.
So I think it's more efficient to do the first method. Also, less you touch the equation, more accurate it is, right?
Yeah.
Anyways, these are some equation solving. Some special feature to be noted is using the PLT-SMLT2 app, right? Which helps you solve the polynomial equation. Also, if you have a systems of equations, like the one that we did yesterday, okay, these are, just to note that these are available. You are allowed to use. Okay. So when you have a polynomial equation, don't go like graphing that. Just use a PLT-SMLT2 application. Same thing for systems of equations. Pretty sure they're a lot easier and faster to use than graphing and then finding the
Twice
point.
long, it's the y.
Oh, thank you.
I don't think it matters. But.
Matters a lot. Yeah, Plysmol too. That's
By
how
the way,
I
are we
use it.
only allowed to use Plysmol 2 in our exams? Because there's so many other apps that even if you erase it, just stays there, you know? Like inequals is pretty useful. Because it does all the, like, you can put x equals and stuff like that. So it allows you to skip a lot of steps in some questions.
I think you're not allowed to use that.
Okay.
But
How
it's
do they control
How
that?
do they control
Yeah,
that?
no, paper 2, our specific graphing calculator is allowed, so anything that comes with that graphing calculator should be allowed, no?
No.
Why not?
Yeah, no, there's a
There's a list of
limited
applications that you
apps.
can have.
Yeah.
I'm pretty sure you can delete the applications on your calculator manually without having to hook up
But
to
the
the
instant
computer.
you reset it, it comes back.
Really?
Actually?
I think so. Like
I don't think so.
like these ones,
Like
these
memory
applications,
clear?
this application.
When you do the second plus 7 1 2.
Yeah, with these applications, yeah. If you have your own app that you program, then it goes away, of course.
Interesting.
But then, yeah.
I'll do a test.
Okay.
Maybe in class time. I'll make a note of it.
We can use them just to verify our
Yeah.
constants.
Yeah, I know. Like one of my job as a math teacher is to be there on the math exam day, and check the calculator. My job is to check the calculator and leave, because I can't be in your
Yeah.
math exam, right?
Oh. Because you're not allowed to answer questions.
Yeah.
Oh.
So I'll be in your French exam. Yeah.
Okay.
Anyways, let's move on. I think I mentioned everything about the equation solving. Okay, now let's talk about the transformation. Transformation of functions.
That like clicks. Like gravity.
The transformation has a basic shape of y equals a times f of b times x minus c plus d. And each of them have a specific role. A is for the vertical stretch, also a vertical reflection. Right? And the B is responsible for the horizontal stretch and the horizontal reflection. C is responsible for the horizontal translation, and D is responsible for the horizontal, thank you, vertical translation. Okay. Couple things to note about the horizontal part is that horizontal parts are counterintuitive, right? These are counterintuitive. What I mean by the counterintuitive is that if you have a positive value of C, it feels like we should be moving to the right. Like, yeah, it's going, wait a second. Let's put plus C here to make it more counterintuitive. Yeah, so it's better if at least all the horizontals counterintuitive, right? So if you have a positive value of C, it feels like we should be moving to the right, but actually it's moving to the left. For the B value, if you have a value that's bigger than 1, let's say 2, it feels like we should be stretching positively, or we should be like expanding, but actually it's the other way, we're actually compressing. So it's important that we know that horizontal stuff are always counterintuitive, so be mindful of that. Also, if you have multiple transformation written in different cases, then the order of the transformation is SRT, where it stands for stretch, reflect, and translate. Okay. So make sure you follow that order. Sometimes you'll see, especially the horizontal part, then it'll be like messy with the fractions and with the brackets and stuff, right? So for example, if you have like y equals to 2, f of 3x plus 3 minus 1, let's say. Like it deliberately tries to trick you here, right? What I suggest, translating is moving. Just moving things. Is that what the question was?
Excuse me?
Is that what the question was?
I was just asking what SRT was. I missed it.
Yeah. SRT, stretch, reflect, translate. So if you have a question like this, what I suggest is just, go to the regular habits of putting things in right places, right? So I'm going to put it as 3 bracket x plus 1. So we save our life. There is a horizontal translation of -1. Okay? It's my pro tip. Like, definitely. You'll see some questions where it's trying to trick you like this. Although I don't think I've seen like you have all A, B, C, D. Actually, that's more common too. Like it's gonna like just hide A and B value, or it's not gonna have D. Then it's kind of confusing too. So.
What is the confusing part about this? Is it like 3 and 1? Like.
Yeah. So it's right now the first one
Yeah.
is written as 3x plus 3 inside the F, right? And it's not really following that bracket representation in the base layer of B bracket x plus C bracket, right? So that's why I put it back into the regular shape that I know.
Why don't we write that as like f negative b x minus c? Then it's intuitive for everything. We just write it that way.
We could have done that. Then would be like f of 1 over b bracket x minus c, right? Sure. If you wish. Anyways, I think we're good for here. It's a heavy topic in Pre-Calc 12, but I don't think it's really important in IB math. Okay, anyways, let's move on to the next part. 2 more. Polynomial function. So this polynomial function part is quite heavy and rich in context. So let's get through this. So first thing that we should know is that, let's say we have a case of, say f of x is equal to ax power of n plus a n minus 1 x power of n minus 1 plus plus a 1 x power of 1 plus a 0. So this is the usual shape of a polynomial function where you have the n values and all the degrees are just, all the powers are just natural numbers. this degree n, okay, it tells you the number of roots. Number of, in this case, number of all roots is equal to n. Right? So that's quite important, you know. So if you can technically you can try to figure out how to factor this, and you'll have n factors, right? Well, sometimes it's going to be repeated, but another thing to note is that, like yesterday, how we discussed yesterday, the complex roots always come in pairs, conjugate pairs. So if you know one, then you automatically know the other one. Right? So you should make a note of that. Another thing to note for the polynomial function is the existence of the sum and product of roots formula. The sum of roots is equal to, in your formal booklet, we have them. The sum of the roots is negative a n minus 1 over a n. Yeah. And the product of roots is equal to negative 1 over negative 1 to the power of n, a 0 over a n. Right. So here we see that the sum and the product are always real numbers, right? So even if you have the complex roots, because they come in conjugate pairs, if you add the two conjugate pairs together, the result is real. If you multiply two conjugate pairs together, the result is also real. So you have to know that fact. Quite often you'll have to use your knowledge about these, how many roots you have, the fact that there are complex roots, they come in conjugate pairs, and the fact that you have the sum of roots and you have the product of roots all together. You use all the knowledge together to produce some kind of answer, right? So hopefully you're able to draw these connections within your brain when you're solving problems. I think there was a question in this type of polynomial function style in the past paper that we did the other day.
Yeah.
It was like Monday, I think, but I didn't go over it. So we'll have a chance to go over this in a question style. Another thing that kind of went through my head, I completely forgot about, was the existence of the remainder theorem and the factor theorem. Right. So what are they? So before we do the what are they, if you see a remainder, if you see the word remainder in your exam, you use remainder theorem. Okay. But what is a remainder theorem? Remainder theorem goes like this. We have a p of x, the polynomial function p of x, and it goes like the quotient of x multiplied by the divisor of x plus remainder of x. Okay. So what we do is we divide both sides by the divisor. The divisor is supposed to be divided, right? So we can do divided by d of x. So p of x is divided by d of x. So then the d of x is usually what's it called? Linear factor. So then we just do the division, polynomial division. So then use q of x here plus remainder over d of x. I think all cases we have remainder as just a constant number, but let's write it like this.
What is p of x represent?
P of x is just a polynomial function.
Q of x is what again?
The remainder.
And why was this useful again?
Why is it useful?
Q is the quotient.
Yeah.
What did I say?
Remainder. You said the remainder.
Oh, sorry.
Q is the quotient.
Q of x is the quotient, yes.
This quotient.
Why is this useful?
When d of x is 0, then that makes that term 0. So p of x is r of x.
Yeah. So if you know, like let's say you try to divide it by a certain factor, then we can find the remainder. Right? So in this case, if d of x is equal to 0, then q of x, d of x is also 0, right? So therefore, sorry, not d of x, d of a is 0. If d of a is 0, then we say p of a is just equal to r, or r, the remainder. So you can find the remainder
Yes.
easily. It's actually the other way, the order of appearance. The factor theorem is when there's no remainder, right? So, factor theorem states that if, probability of A is P of A is 0, is equivalent of saying that, what is it? D of x. How to explain this again?
There's like factor theorem.
Yeah, factor theorem. I'm spazzing out. I need water.
Why is that useful if the divisor is 0? Then the whole thing just equals the
You'll see a question like, you're given a function, and then you know the remainder, and then you're asked to find the divisor. Or if you know the divisor, you're asked to find the remainder quickly. Then instead of doing the division yourself, you can just compute p of a, and then you just find the remainder right.
And how can a divider be 0?
Yeah.
If d of a is 0. So if you divide by 2x plus 3, or that was a bad example. 2x plus 4. If your a is negative 2, then it will be 0, right? Yeah.
Makes sense.
Because you're dividing by not like one number, by like a function.
Okay, let's go back. How do I explain the factor theorem again? Let's try again. Factor theorem is basically when we have the remainder is 0, right? So we know that p of x is equal to the q of x times the d of x, right? And d of x usually comes in the shape of p of x is equal to q of x times x minus a. D of x usually looks like that, as a linear factor. So at this point, I know that p of a is going to look like this, like q of a times a minus a. So it's going to be 0, right? So a minus a is 0. So this means that, okay, so I think I know. P of a is equal to 0 if and only if d of x, or x minus a, is a factor of p of x. Okay, does that make sense?
Yes.
If p of a is 0, it means that x minus a is a factor of p of x, because there's no remainder, right?
What if q of a is equal to 0 and it's not like,
If q of a is equal to 0,
yeah.
then it means that q of x has that x minus a together as well, x minus a factor as well.
Okay.
Then we say that it has a factor of x minus a squared.
Twice.
Yeah, twice.
Okay.
I've never thought of it that way.
I have right here.
It's kind of confusing.
I should.
Yeah.
I feel like it makes more sense when you have real
I'll try to find the question related to this in the past paper. I'm pretty sure it'll appear. Anyways, n degree, nth roots, complex roots are always conjugate pairs, polynomial division, polynomial division and then factor theorem, remainder theorem. A polynomial division, just to recap quickly, let's say we have like 2x squared plus 3x minus 2, and then we can divide it by, like, let's say x minus 1, for example. Then we just do the kind of a long division kind of thing, but we just do with the x, right? So it'll be like 2x squared minus 2x, and then it's going to be like 5x minus 2 plus 5, 5x minus 5. So it's going to be negative 2 minus negative 5, positive 3. So this one has a remainder of 3, and the quotient is 2x plus 5, kind of thing. Okay? That's how we do the polynomial division. But I think that's about it for the polynomial function. Can we move on to the next part?
Yeah. Inequality.
Inequalities. 10. Inequality. Okay. I'm quickly losing my tension. I want to go home so bad, but I'll try to keep on to it.
This is the last one.
There's one more. Absolute function. It's okay. Inequality. So inequality is when you have like f of x is, let's say, less than or equal to g of x, for example, right? Basically what we want to do is we want to, first thing we want to do is we want to find the solution, right? We want to find the equation. We want to find the solution of the equation. So first is you solve f of x is equal to g of x, right? And then use the points, use the solution to test the points before and after. So I'm going to test some points before the solution of this equation, and then I'm going to test some points after. Or maybe if there are multiple, I'm going to test the between points as well. And then for each of them, I verify whether the inequality holds true or not. Right? So that's one way to do it without the graph, obviously. If you want to solve it graphically, there is a function, there's a method where you go to y equals and then you scroll left, and then you can select various other types of equations. By default it's equation, but you can scroll, like you can press enter multiple times to either go like positive or like greater than or less than kind of stuff.
Can you do that in IB exam
Yeah.
for that function?
It's just y equals function. Y equals method.
That's an app though, right?
It's not an app.
Oh.
It's a default.
Oh.
And then you can scroll left. You can press enter multiple times.
Well,
Does
I
it?
don't know what that does.
Yeah, you can do trial and error. So line. See how you can go like these?
That's just the shape of the line.
Yeah, but like you can see like it's shape. So you can use that too if you want. You have to be good at it.
I have to shade that everything.
You have to understand how it works.
I don't understand how that works.
Also, you can do this if you are trying to find an inequality. If you're trying to show the inequality of, let's say, like y is greater than f of x kind of thing, then you do the similar thing. You graph y equals f of x, and then test points in regions. Then shade the true side. Right? So you're going to test a point that is, obviously not on the graph. For example, 0, 0 is an easy one to use. Plot in 0, 0, and then see if the inequality holds true. If it's true, you shade that side. If it's false, you shade the other side. Okay? So that's the way of how to graph this kind of inequality. Yeah. Maybe I should have talked about this first, but if you have just like an easier one, what you can do, let's say f of x, let's say it's like less than 0, for example, then represent f of x equals 0 on number line, and then you can also try to test points before and after. So that's kind of using a number line representation. The first two variations are Cartesian plane kind of thing.
When you're graphing, is it like a dotted line for the greater and equal to?
Yeah,
Solid.
yeah. So if it's greater than or equal to, like for example, it's going to be like dotted line and then shaded, right? For, let's say, greater than or equal to. Right. Whereas,
Do you shade the part where it isn't, like?
it is, where it is true. If it's like this, then it's not equal to. Like, sorry, not included. Right? Makes sense?
Yeah.
What? Oh, it's equal to.
The first one, f of x is less than or equal to g of x kind of thing, is more useful. Like if you have like, it's gonna look something like this, right? You have like this, and then you have like this, and this is f of x, and this is g of x, right? And then you find the intersection points, these 2 points, and then obviously f of x is less than g of x, so we shade the inside part like this. So f of x is less than or equal to g of x. So this is a graphical representation. So if I know this point is to be A, if I know that this point is to be B, then we know that f of x is less than or equal to g of x when x is between A and B, kind of thing. Right? So if you solve it, it's x is between A and B. What an example. I think it looks a bit better. Right, we're going to do the last one?
Yeah.
Okay. Absolute value. Absolute function. Okay, so we have 2 types of absolute function, where we have the absolute of f of x. This is the most easier one, right? So when you have an absolute value of f of x, then what we're doing is we're reflecting over the x-axis, right? So you'll see a graph of what it's supposed to be. A function like this will have the shape of reflecting over the x-axis. So everything stays positive. So I can name this to be no negative.
And you do the piecewise to
Sorry?
represent that graph. You can do the piecewise function.
Piecewise function, yes, you can use the piecewise function too. So it's going to be f of x, negative f of x, and f of x. Okay. So that's what the absolute function looks like. Whereas the other one, absolute function of absolute value of x. So we have this weird shape as well. This one, although it just seems like, okay, now we just do the reflecting over the y-axis, right? So it's not really the same. It is true that we're reflecting over the y-axis. But it's not going to be like no negative. I think it's just be like copy the positive side. Right? So for example, let's say I have a graph that's supposed to look like this. Should I use like a weird function? Let's say I have a function that's supposed to look like this. Then if I take a function of absolute value of x, then it's just going to copy the positive side on the other side. So I'm going to reflect it over the y-axis. Okay. So it's not like there's no negative kind of thing, right? It's quite different. It's a different understanding. We just copy whatever there is on the positive side, and we put it on the left-hand side. Okay. Right, I think those are some absolute function stuff. Any questions about the last part?
Just quick question.
Yeah.
To get the oblique asymptote, we just do polynomial division, right?
Yeah.
For the shading for inequalities,
Yeah.
is there any other special things that we have to know? Because I remember I got that question wrong on the test last year.
Because you like we didn't use dotted lines, we used solid lines.
When do we use dotted lines?
When it's not equal.
like not equal, right?
Yeah, less than
Okay,
equal.
yeah.
Yeah. Dotted line for non-inclusive.
And that's it. That's
Solid line for inclusive. Yeah. Okay. Otherwise, thanks for staying around another day. Good luck. Good job for me too as well. All right. Thank you.
Did you make this